Okay, so let's proceed with our discussion to talk about Born Haber cycles. Hopefully, you're now familiar with the different types of energy changes that you are going to come across in these Born Haber cycles. So, what is a Born Haber cycle? A Born Haber cycle is useful to calculate lattice enthalpies. Why is this important? Because we can't calculate this energy change directly from experiments. So let's look at how a Born Haber cycle is structured. So we're going to look at how you can calculate energy changes from experiments, from experimental data. It's possible that you can figure out, for example, the enthalpy change of combustion from an experiment. So I'll do a video where I will explain how this is done. But there's a limit to the energy changes that you can figure out using experimental data. For example, this type of energy, you can't calculate it directly from experiments. So you can use experimental data and construct a Born Haber cycle and then create an equation that enables you to calculate this. So let's look at how a Born Haber cycle is structured. Okay, so we're going to be looking at a Born Haber cycle for lithium chloride, the formation of lithium chloride. So we are going to start off here with our constituent elements in their standard state. So lithium is a solid here, a metal, and you have your chlorine, which is in gaseous form. So the first label there, you see immediately below this energy level here, we have this product that we want to form our solid lithium chloride. So this is, remember, this is an ionic compound, so it's going to have a solid ionic structure or a lattice structure. So this energy change from constituent elements to this product or lithium chloride, that would be your enthalpy change of formation. And the fact that your reactants are at a higher energy level than the product shows you that the reaction is exothermic. In other words, these reactants are going to lose energy as they form this product. So the product is at a lower energy level, the reactants are at a higher energy level. This tells us that for us to form this product, which is at a lower energy level, we have to lose energy. The high energy that is in these constituent elements has to be lost in order for us to descend from this level to this level. So losing that energy into the environment is what makes this an exothermic reaction. So take note of that. But it's also possible to form our lithium chloride in a different route. So what can you do other than just this direct energy change from your constituent elements to the product lithium chloride? So there are some energy changes that can take place, which we're going to explore. Okay, so what are the changes that these two constituent elements have to go through in order for us to come here? So we're going to look at a path that we can follow all the way down to this product here, rather than just looking at this direct path. So this doesn't tell us much of the changes that are taking place. So we're going to explore the actual energy changes that are taking place all the way until we form this product. Okay, so if lithium is in solid form like this, we have to, just generally speaking, we have to have our lithium plus, it forms a charge of +1 ions, and our chlorine minus ions, and this bond in an ionic bond to form your lithium chloride. So we're going to look at how you form these ions. So if we look at this from here to here, what has happened? We see that we have half a mole of chlorine, and we now have 1 mole of chlorine atoms. This was a half a mole of the chlorine molecule Cl2, but now we have Cl. These are individual atoms. So there's a change that has taken place here to form 1 mole of chlorine atoms in gaseous form. So that would be the end of change of atomization of chlorine. For the lithium, there is not yet any energy change that we are showing there. So let's move to the next stage. In the next stage, you have to show the energy changes that take place in lithium. So for lithium, it's in solid. If we convert that to gaseous atoms, that would be the enthalpy change of atomization of lithium. And take note here that it's endothermic. You need to supply energy in order for you to break off these atoms from this solid lattice here. And the atoms need to break off as individual atoms, and so that requires energy. You need to overcome the forces of attraction that hold the solid structure together. So this is what makes it endothermic. You are acting against the forces that hold the solid structure together. So it's endothermic. And check here that our enthalpy change of atomization of chlorine here was also endothermic, because you're actually breaking these bonds and ending up with individual atoms. So these are endothermic changes. So now that you have your gaseous atoms of lithium and chlorine there, the next thing is you need the ions. So let's show here the energy change that takes place here for lithium, from lithium in gaseous form here to lithium plus 1 ions in gaseous form. That would be your first ionization energy of lithium, and this energy change is endothermic. You are pulling off electrons from the lithium from the attractive force of the nucleus, so you require energy to do so, and that makes this energy change endothermic. Our lithium plus ions are still in gaseous state there. And then you have your chlorine, which you also need to turn to chlorine minus ions. So you can do that in that next step. So remember, these electrons are then accepted. This mole of electrons is then accepted by the chlorine atoms. This is what you are told the first time you are told how these ionic compounds are formed. So when chlorine atoms accept electrons, this will be the first electron affinity of chlorine to give us our Cl minus ions. So you now have these two ions, your cation and your anion, both in gaseous state. So these can now combine to form your solid lattice structure. So this energy change here from here to this solid here is called the lattice enthalpy formation of lithium chloride. So it is this energy change that we cannot determine. Like we said here, you can't you can't calculate this directly from experiments. So you need data for all these other energy changes, and you manipulate that data in an equation to figure out this energy gap here. So let's look at an example here. So we're going to look at Hess cycles later on. So the basic law here is that this energy change here that takes place here, this arrow, the enthalpy change of formation, is equal to this energy change plus this energy change plus this energy change plus this energy change plus this energy change. So you have to add all these other energy changes and equate that to this energy change. So the energy change is going to be, the overall energy change is going to be the same regardless of the route taken. So we'll look at Hess law later on when we talk about Hess cycles. So this is basically the law that's at play here. The energy change going all the way up here and down is the same as this one. So you can create an equation there. Let's look at a specific example. So you're given a table here of the enthalpy changes of the different enthalpy changes, and the question here that we would like to tackle is we want to calculate this here. Calculate the lattice enthalpy change of formation of lithium chloride. So let's plug in the values that we're given here. So we are told here that the enthalpy change of formation of lithium chloride is a negative enthalpy change, meaning that it's exothermic, negative 409 kilojoules per mole. So let's put that on the diagram. That's your negative 409. Then you are also given the enthalpy change of, so in this stage, what's happening? We saw that this is the enthalpy change of atomization of chlorine. So enthalpy change of atomization of chlorine, 1 mole of chlorine is 242. But here we have half a mole. So we have to divide that by 2 to get 121. So that energy change from here to here